let's do some more example problems here with enthalpy. Let's look right away here at example 3. Says the equation and the enthalpy change for the reaction between an unknown gas D and fluorine gas are given below. So we can see that delta H, negative 250 kilojoules per mole of reaction, like always. How much heat is released when 4 moles of fluorine react with excess D? So again, normally if they gave us grams, the first thing we would do is convert those grams to moles. So we're going to start with moles because that's what they give us. So 4.0 moles of F2. And then from the balanced equation, we can see that 2 moles of F2 react for every 1 mole of that reaction happening. So 2 moles of F2 for every 1 mole of that reaction. And then in 1 mole of that reaction, now we're coming here, there's 250 kilojoules. And it's negative, so that is, again, how much heat is released means they want your answer to be positive. So 4 divided by 2 is obviously 2. 2 times 250 is 500 kilojoules is the correct response. Okay, and now remember that this right here, remember just kilojoules, we could call that the Q value. Okay, that would be Q, where delta H, remember, is always kilojoules per mole of reaction. Okay, example 4 says the enthalpy of reaction when NO reacts with O2 is shown below. Calculate the quantity of heat released when 73 grams of NO is converted to NO2. So here's when we're starting with grams. So we've got 73.1 grams of NO. And then now we've got to convert our grams to moles first of all. So nitrogen's 14, oxygen is 16 in terms of molar masses. So that's 30. So there's 30 grams in 1 mole of NO. And then based on the balanced equation, we've got NO, right? So we've got 2 moles of NO that react, and every time they react, that is 1 mole of that reaction happening. And then we go to our delta H value. 1 mole of the reaction releases 114.1 kilojoules of heat. And again, the question is calculate the quantity of heat released, so we want our answer to be positive. 73.1 divided by 30 divided by 2 times 114.1 equals 139 kilojoules of heat would be released. Okay, now let's go back to question number 1. Okay, notice in all of the examples that we've done so far, they've only given us 1 reactant. Okay, they only gave us this amount of NO. This is how much NO you have. Well, what do you assume then? Well, you assume that O2 is therefore the limiting reactant. They don't tell you that, but you just have to assume that. Okay, but what if they give you an amount of both of the reactants? For example, going back to example question number 1, in example number 1, they had said that we had 32.6 grams of F2 that reacts with excess N2. Remember that. But what if it said you have 32.6 grams of F2 that reacts with 25.4 grams of N2 to produce NF3? Calculate the amount of heat released. We have to ask ourselves which of those two is more important, and really what matters is when will this reaction stop releasing heat? Of course, when the reaction stops. And when will the reaction stop? Whichever one of those two runs out first. So therefore, this is now a limiting reactant problem where the first thing we have to do is figure out which of those two is going to run out first and then use that one to now answer the question. So the first thing I'm going to do is I'm going to take 32.6 grams of F2 and I'm going to use the molar mass, 38 grams in 1 mole of F2. And then I'm going to need to use the balanced equation to go from moles of F2 to moles of N2. So I come back up here, and for every, here it is right here, 1 mole of N2 reacts with 3 F2s. So 1 N2, 3 F2s, and then 1 mole of N2, and then the molar mass is 28. So now I can take 32.6, divide by 38, divide by 3, multiply by 28, and I get 8, basically, 8.01 grams of N2. So remember, that's how much N2 I need. This is how much N2 I have. I have plenty of N2. Okay, I'm not going to run out of N2. That it means I am going to run out of F2. So that means that F2 is the limiting reactant. So to solve the problem, remember up here we started with our 32. Basically, it's just the same problem again. It's this right here. Okay, how much heat is going to be released? Still the 75.5 kilojoules. Okay, let's go ahead and look at example 6. A student performs an experiment to determine the value of the enthalpy change for the reaction represented by the balanced equation below. We've got 3 different solutions, 1, 2, 3 reactants, 1, 2, 3. Using the balanced equation for the reaction and the information in the table above, determine which reactant is the limiting reactant. Okay, and we can see that for every 1 Na2S2O3, 4 NaOCl's are going to react and 2 NaOH's are going to react. Well, since the concentrations and the volumes are the same, that also means the moles are the same. So which one's going to run out first is the one that we have that's going to react more moles than the other ones are. So 4 moles of NaOCl are going to react for every 2 NaOH's and for every 1 Na2S2O3. So therefore, NaOCl, without even doing any math, is the limiting reactant. Okay? And you would explain that by saying, since the moles are equal, and there's a 4 in that balanced equation, then it's going to be the limiting reactant. Okay, and then part B here, the solutions all originally at 20 degrees Celsius are combined in an insulated container. The temperature is moderate, as shown in the graph below. Okay, according to the graph, what is the temperature change in the reaction? So first of all, it starts at 20, and then where does it end? That's the question. So here's 32, here's 34, so that means that's 33. So remember, always go 1 digit beyond what you know. So I would say, again, roughly that's probably 32.5 minus 20 equals 12.5 degrees Celsius. Okay, yep, it's that easy sometimes. Okay, and then C, the mass of the reaction inside the calorimeter is 15.21 grams. Calculate the magnitude of the heat energy in joules. So whatever they just say joules, remember that's Q, not delta H. That's the Q value. They give us the specific heat, they give us the mass, and we just calculated the temperature change. So Q is just equal to MC delta T, which is going to equal 15.21 grams times 3.94 joules over grams Celsius times the temperature of 12.5 degrees Celsius. So 15.21 times 3.94 times 12.5 equals a Q value of 749 joules. Okay, and when they say the magnitude, that just means how big it is. It doesn't mean you don't have to be negative or positive there. Okay, and then part 2 is the last part here. Says using the balanced equation for the reaction and your answer to part A, calculate the value of the enthalpy change for the reaction in kilojoules per mole of reaction, including the appropriate algebraic sign with your answer. Okay, so first of all, let's think about the sign. The temperature went up. It was 20. It goes up to 32 point something. That is releasing heat. So we know, first of all, that the algebraic sign is going to be negative, okay, without even thinking anything beyond other than that. Okay, and now we can come back up here and we can say, okay, well, in the balanced equation, the limiting reactant was NaOCl. And we have 0.5 molar and we have 5 milliliters of it. Okay, so we've got 0.5 molar and we have, how many was it? 5 milliliters, which is 0.005 liters. So that's molarity. And that's going to get us to moles of NaOCl. So that's half of that. So 0.0025 moles of NaOCl. Okay. And then we can say, because remember, they want moles of reaction, not moles of NaOCl, moles of reaction. So from the balanced equation, we can see that again, getting all that there are 4 NaOCl's that react per reaction, per 1 mole of reaction. So we're just going to say 4 moles of NaOCl, 1 mole of reaction, and that's going to get us a number. So 0.0025 divided by 4 equals, so that's 0.000625 moles of reaction. And then our joules are 749. And if you want, you can, that's a conversion you can do in your head really, really quickly. 749 joules is 0.749 kilojoules. So just to make it easier, because they do want it in kilojoules, anytime you go from meters to kilometers or joules to kilojoules or liters to kiloliters, something like that, you just move that decimal point 3 spaces to the left. Okay, so that's 0.749 kilojoules. So 0.749 divided by that 0.000625 equals 1,198 kilojoules per mole of reaction. And remember that is remember the algebraic sign, that does need to be a negative, okay? And that is your final answer.